in many cases, we might have to share the medium. Right, so this is what I'll talk about next, is medium sharing. If we have to share the media, there are two more topics I want to talk about. One of them is media access control. Media access control really is the time when data is shared, or sorry, the medium is shared. So if we have let's say the example of a bus topology or wireless communication. If one machine wants to transmit data to the others, in the case of wireless, then this machine would transmit a electromagnetic radio signal to everyone. When this one wants to communicate, it will transmit a radio wave wireless electromagnetic signal to everyone. And they must be transmitted on the same frequency, because everybody is receiving on one set frequency. But if these two machines transmit at the same time, we're going to have collisions. Similarly, this is very similar to the bus topology. If this machine wants to send data to this machine, the signal will go all the way to all ends of the network. If this machine wants to communicate with this machine, it has to wait for this one to finish. And if it transmits at the same time, then we're going to have collisions. And hence, in all local area networks of this sort that share the medium, some sort of control is required, and it's called the media access control. That's controlling which machine can transmit now. So there are a number of media access control protocols that were used. So I'm going to go through them now briefly, and the first one is called time division access control. Time division access control, and that's every time between all the machines, for example, that need to transmit. Let's say we had 4 machines. We say every time, say every second, for example, every data unit that we want to transmit, we split it. Time is split into time slices, and every user or every machine is allocated that time slice. And it's only allowed to transmit through that time slice. So for example, if there are 4 machines, here's 1 second, 1, 2, 3, 4, 5, 6 machines, then we split the second into 6 time slices, and each one, the first machine transmits at this time. All machines here, they must be synchronized together. So that means their clocks work together. The clocks tick together. And every time the second ticks, then we know who's going to transmit first, and then it stops, and then the second one transmits and then stops, the third one. And there for 10 machines, then for example, each one will transmit for 1/10 of a second. So that's a real easy to implement. Absolutely easy, no overheads. Computers are good. So first thing, is there overhead? Are there overheads? For this is the time division access control. No overheads, which is it's a big advantage. Is it likely to get collisions? No, not if every machine sticks to the timing, to its time, no collisions, which is fantastic. Another good point. There's something called starvation. What's starvation? If a machine doesn't get the chance, its turn to transmit for a very, very long time. In this case, no, we never have starvation. Every machine will get its turn every second, or even less than a second, but everyone. So it looks like it's a good system. What about utilization of channel? What do we mean by channel utilization? What's that measurement? Anybody knows what it is? What's the measurement of utilization in general? Any utilization? Yeah?
How much of the available bandwidth the device is utilizing?
Yeah. It's the percentage of the used amount compared to the total amount. Like if Ryanair flies an airplane that carries 100 passengers, but it only takes 80 passengers, we say the airplane is 80% utilized. Okay, so its utilization is what is the percentage of the used in relation to the total amount. So on channel utilization, if your channel can transmit 100 million bits per second, but you're only transmitting 50 million bits per second, then you're only 50% utilizing that channel. So what about utilization here in the time division media access? See here, everybody has their time sliced to transmit. Most computer communication, they don't really use or utilize all the time allocated to them. So if we have 10 users and only one user has lots of data to transmit and the others are not using, they don't have any data to transmit. So in this case, this user can transmit during the time allocated to him and then has to wait. Then user number 2 has no data to transmit. The channel is not used. User number 3 is not transmitting. So the channel is probably not used and may lay unused. And yet we have a user who has had lots of data to transmit. So channel utilization in time division is not great, poor. That's one poor. Unless everybody has a lot of data to transmit all the time, then the channel will be utilized 100% of the time. But unfortunately now it's not. So that's known as time division. We'll look at other features of the time division at the next time now, as we keep going. The next one is called the token. The token, we talked about it maybe when we talked about topologies. So the token is used as a way of controlling who can communicate. See, what we need is that we don't want two machines communicating. With time division, no two machines will ever start transmitting. With the token, we say we have a small frame, it's maybe only 3 bytes long, and we say we send it from one machine to the next and we keep circulating it all the time. It keeps going around from one machine to the next. And the protocol says if you have data to transmit, first wait for the token. After you receive a token, destroy token. Send data. When you finish sending your data, then create a token. Generate new token. And pass it to your neighbor. So if you have data transmit, you don't just go ahead and start transmitting. No, you're not allowed. Wait until you get the token. So maybe someone else is transmitting, and when they finish transmitting, they send the token. So the token is going around. So when you get the token, this is what the protocol says. First destroy it, send your data. Why do you destroy it? So we make sure there's no token floating around. Destroy it, send your data, and when you finish sending your data, generate a new token and send it to your neighbor. So how good is this? Does this work? It works in some networks. So this is called the token. How good is it? Overhead, does it have any overheads? Yeah, it has some overheads. It's the token. That's a little poor, bad idea. Does it have collisions? No, not if we use this system properly, and that's a good thing. Is it possible to have starvation? No, because the token is circulated. Everybody will get the token in turns. Channel utilization is reasonable. It's good. It's better than the time division, because the time division, if 9 users have no data transmit, only 1 user has data transmit, can't use it. The channel will remain idle, and yet we have data transmit. But in this case here, the token will fly very quick and come back to the sender, so we don't waste a lot of time. So better. Channel utilization is not poor, it's better. And it's slightly better than time division. Now, sometimes here, with the token, if this machine has data transmit, waits for a token, got a token, destroy the token, send data, just about to generate a token, and somebody turns the machine off. So the machine is switched off, and there's no token. The token is destroyed. It hasn't generated the token yet. So it leaves the network without a token. So we could end up without any token. And that can destroy the communication. They call this single point of failure. Any system that has a single point of failure is a bad system. This one, the token is a single point of failure. Yes, and it's the token, and that's a very bad point. With the time division, no, there's no single point of failure, and that's a good point for time division. Then, the next one we look at is called polling. And polling is all these machines that we have in the network. One is allocated as a master, so it operates as a master-slave kind of orientation. This machine, we say you are in charge of the channel. So this machine sends to this machine, says, do you have data transmit? If you do, go ahead, start transmitting. When it finishes, it'll ask this one, do you have data transmit? This might say no. Well, then we ask the next one. Do you have data transmit? No. Well, then ask the next one. Yes, we'll go ahead and transmit, and then we ask the next one. Then we go back and start polling the first one second. So polling is requesting, asking these machines, now it's your turn. You can transmit now. Do you have data? If you have no data transmit, we won't waste time. We go to the next one. Fairly similar to the token bit. So this is called polling. Does it have overhead? Yes. It has a master-slave thing. Collisions can happen? No. No collisions can ever happen. Starvation? No, because we go around in turns. Is there channel utilization? Is fairly good. It's better than time division. Single point of failure? Yes. And that's a bad thing. That's just this master machine. If it fails, nobody can transmit, because nobody is allowed to transmit until given the permission by the master machine. Finally, well, not finally, number 4 is carrier sense multiple what? CSMA access. So carrier sense multiple access. It's known as CSMA protocol. This was introduced, and it's very simple protocol. It says, listen to the channel. Now you only have 2 conditions. Either somebody is transmitting or nobody is transmitting. If free, if quiet, the channel is quiet, the channel is free, then send. Transmit. Else, if busy, wait. Or go to sleep for 5 milliseconds. And go back to number 1. And listen again. Listen. Is it busy? Somebody is transmitting now? Well, then go sleep for 5 milliseconds and then wake up. Listen again. Is it free? If it's free, now you can transmit. Those 3 here are classified as taking turns. take your turn kind of protocol, those 3 protocols. The next 2 protocols are random. There are no turns here. With the first, second, and third, every machine will get their turn, one after the other, in some order. You're not going to be left starved. But with this one, you could listen, and you find it busy, you go to sleep, and the guy finishes transmitting. Someone else comes in and finds it while you're asleep and waiting. Another machine comes in and finds it free. They start transmitting. You wake up, you find it busy again. You go sleep for a short period of time, same thing happens. You could end up not getting the line. If you are very unlucky, you may not get the line for a long time, and that's called starvation. So CSMA, does it have overhead? No, almost no, very little. No overhead, because you just listen. If it's free transmit, there's no program, so it's an advantage. Let's go with starvation. Is it possible to have starvation? Yes, that's a big problem. Channel utilization, it's reasonably good. We'll see. Single point of failure? No single point of failure. That's another good point. There's no token, there's no master machine. Are there collisions? Is it possible to have collisions here? If 2 machines get the request from their user's command to transmit, and they both listen to the channel, and they both at the same time find that the channel is free, then they say, great, channel's free. They both start transmitting at the same time. And that's the problem. So, big problem. Yes, we have collisions. We can have collisions because there's nothing controlling the collision. All we say, listen, and if the channel is free, transmit. If 3 machines listen at the same time, and they find the channel is free at the same time, and they start transmitting at the same time, then there's collision. So there's a problem of collisions here. And the problem here is when they start transmitting their frame, each one of them thinks, I'm transmitting my frame. So it keeps on transmitting for a long period of time until they finish transmitting the frame. And every other machine can't understand what's being transmitted because there's more than one machine. And we call that collision, and time-wasting collision as well. So if you have collisions, you have poor channel utilization as well because of the collisions. You did good channel utilization. No, it's poor channel utilization. Because the fact, every time you have a collision, all the time is wasted. While 2 or 3 machines transmitting, they thinking everything is okay when it's not. So then finally they introduced another protocol, and they called it, same name, carrier sense multiple access with collision detection. The protocol says, listen to the channel. If busy, if someone is transmitting, then wait for a little period of time. Sometimes they don't wait. They go on and then go back to the listen again. Sometimes they don't wait. There's no sleeping time. If it's busy, listen again. If it's busy, keep on listening until it finishes. They call that persistent wait. So you're listening all the time. If you go to sleep for a little while, it's non-persistent. Now, that's step number 2. If it's busy, then wait. Else, let's say it's free. The channel is free. If it's free, then send your data. Transmit. Start transmitting. But also, start listening or keep on listening. Start listening to your message. So you send and you listen at the same time. if there is a collision, if collision, how do you know if there is a collision? See, if you send ABC, if you send the message ABC, and when you listen, you get message ADBM. That's not the message you are sending. You should be hearing ABC. If you hear ABC, then there's no collision. Everything is fine. But if you send one message and you hear a different message, that means someone else is also talking. So there is a collision. So if there is a collision, what do? Go to sleep. If there is a collision, go sleep. Generate a random number. Generate random number. Random number or. And then go to sleep for a length of time or. And then go back to the very start. So this is the carrier sense multiple access with collision detection. You listen to the channel. If it's free, start transmitting. And transmit and listen at the same time. Keep talking and keep listening. If what you hear is what you say, then there's no collision. Keep on doing it. And if you hear different message, that means there is a collision. You generate a random number between 1 and 10. Let's say 7. You go to sleep for 7 milliseconds. And then wake up and go and listen again. That means someone else is also transmitting. Yes, sir?
If two devices have a collision, do they both go to sleep or is it just
one
go to sleep?
No, both. They both should follow this protocol. They both transmit and listen. And each one of them will hear something different to what they're sending. So they both stop, generate a random number between 1 and 10. I generate a number at 7, you generate number 3. So you go sleep for 3 milliseconds, I go sleep for 7 milliseconds. You wake up first, you go and listen to the channel. If it's free, you start transmitting. I wake up a little bit after you. You've already started transmitting. I listen and I find it busy, I have to wait.
What happens if we both pick random number 7?
Then we, hopefully while we're asleep, maybe someone else would go and listen to the channel and find it busy. Then there'll be no problem. But if nobody transmits and we both go sleep for the same length of time and wake up and listen again at the same time, we find it free, start transmitting again, we have another collision. So it's possible that we have multiple collisions. So this is called carrier sense multiple access with CD. What's the advantage of this over the carrier sense multiple access without CD? Collision can happen, but if it happens, we stop it immediately. We don't waste the channel. So we have better channel utilization. With the carrier sense multiple access without collision detection, if a collision happens, both machines keep on transmitting, thinking they're sending good data when they're not. So they waste the channel for no good. So does it overhead? No, or very little. So that's a good thing. Does it have collisions? Yes, it can. But this time we can deal with it, solved, stop it immediately. So it's not as bad. It might be a little bit bad, but it's not as bad. We don't waste any time at it. So that's good enough. Are we likely to be starved? Yes. If you are unlucky, you can be starved here. You can never be starved with the take turns. Channel utilization is very good, better than possibly most of the others. Yes, fantastic, very good. Single point of failure? No. So these are the 5 protocols you need to know. You need to know how to describe them. So what does the protocol involve, as in, say, the token? What's the protocol? Wait for a token, destroy it, send your data, generate a new token. With the carrier sense multiple access, 2 or 3 steps. Listen, if it's free, transmit. If it's not free, go back to listen again. Maybe it involves sleeping before you go back to listen again, whether it's persistent wait or not. Then carrier sense multiple access has the longer kind of protocol. Now, right, tell me something else. With the media access protocols, which protocol is better? We looked at 5 protocols: the token, the time division, the polling, carrier sense multiple access with collision detection. Which one is better? And why, of course, yeah. In your view.
CSMA with collision detection.
Why? Why is it better? Does it not? It has no collision?
Because it's very good utilization of the...
It gives what? Better or good, yeah, channel utilization. What's the problem with it? What's the disadvantage of carrier sense multiple access with collision detection? It's what? Starvation. Why? What kind? Okay, why is there starvation?
You can get a roadie and never get your return to transmit.
Yeah, because it's randomness. Because the randomness in it, in choosing devices, that you may not get your churn very quick. Okay, guys, thank you very much. See you. Thank you.